Imagine this, the CEO of OpenAI tells a room full of Stanford students that the technology behind ChatGPT is probably going to be replaced. That's not a normal Tuesday. That's the guy who built the thing, whose entire company runs on it, basically going, yeah, we're not done yet, not even close. And look, I don't want to be dramatic about it, but I also don't want to undersell it, because if he's right, and I think he is, the next few years are going to be genuinely wild. We're going to talk about what Sam Altman actually said, what it means technically, and then run through some other releases this week that I think deserve way more attention than they got. So let's get into it. So Altman went back to Stanford, gave this pretty open talk, and dropped a line that I cannot stop thinking about. He said something along the lines of, he's willing to bet there's a new architecture out there and that finding it will be as significant as transformers were over LSTMs. Now, if you're not that deep in the ML world, here's the short version. Before transformers, the dominant approach was LSTMs, or long short-term memory networks. They worked. Then, in 2017, a team at Google published a paper called Attention is All You Need, and practically overnight, LSTMs became the old way of doing things. Every major AI system you use today, such as ChatGPT, Gemini, Claude, and others, they are running on the 2017 breakthrough, every single one of them. And now Sam Altman is saying there's another leap like this waiting to be found. Now, what got me even more than the claim itself was the second part of what he said. He basically told researchers to use the current models to find the next one, which is kind of a wild idea when you sit with it. The AI we have right now becomes the research tool to design whatever replaces it. It's recursive in the way that feels almost too clever. There's a real technical reason this matters too. Transformers have a scaling problem that doesn't get talked about enough. If you make the input 10 times longer, the compute cost goes up 100-fold. It's quadratic. That's why these frontier models cost a fortune to run. It's not just server bills, it's fundamental constraints baked into the architecture. The alternative that researchers are most excited about right now is state space models, like Mamba for example. Instead of attention, they use differential equations to track how information changes over time. The scaling is linear instead of quadratic. Longer context, same cost. That's a different category of capability, and not a marginal upgrade. Now here's where I land on this. I personally think Sam Altman saying it out loud publicly to students, that's deliberate. It's a signal. Stop fine-tuning what exists. Start hunting for what comes next. And that genuinely excites me, because every time this field has made a shift like this, what came after was better than anyone expected. Now, apart from this, Apple Research dropped a paper this week called LiTo, Surface Light Field Tokenization, and I feel like barely anyone talked about it, which is a shame because it's remarkable. The thing it does, you give it one photo of an object, and that's just one photo, and it reconstructs a full 3D version of that object, including how light reflects it, how highlights shift when you change the viewing angle, all of it. Not just shape, but actual realistic lighting. Most methods for 3D reconstruction either need a bunch of images from different angles, or they handle geometry and completely ignore the lighting. LiTo does both from a single image and actually gets the light physics right. LiTo achieves human-level accuracy in depth perception. The technical approach involves encoding the object into what they call a 3D latent space. I'll try to explain it as simple as possible. A 3D latent space is a compressed mathematical representation of both shape and how light interacts with the surface. They trained on thousands of objects from 150 viewing angles and 3 lighting setups, using random subsets each time, so the model had to generalize rather than memorize. I keep coming back to the applications here. Correct 3D plus correct lighting from a phone camera. That's AR that actually looks good. That's product visualization that doesn't need a 3D artist. That's game asset pipelines. It's research right now, but this is exactly the kind of foundational paper that becomes a product in 2 years. Apple doesn't publish things like this by accident. Now, Manus also launched something called My Computer this week, and this one is worth paying attention to. Up until now, Manus was cloud only. You'd give it a task, it run somewhere on a remote server, and you'd get results back. Fine for a lot of things, but your actual workflow, your local files, your dev environment, your apps, none of that was accessible to it. It was always working at arm's length for your real stuff. My Computer closes that gap. It's a desktop app that lets Manus run terminal commands directly on your machine. It can read and edit your local files, open and control applications, use whatever you already have installed. It doesn't matter if you're working with Python, Node.js, Swift, or Xcode. You've got a GPU that's sitting idle, and it can use that too for local inference or training. They demoed building a real-time translation and subtitle app for macOS, all through terminal commands, Manus handling the code, debugging, and then packing. That's not a toy demo, that's real workflow. The approval system is smart. Every command needs your explicit sign-off before it runs. You can set always allow for things you trust or manually review each one. You're still the one deciding. Manus just does the execution. What's striking to me is the timing. In roughly 3 weeks, you have Perplexity, Nvidia, and Manus all ship local AI agent products. The race moved from the cloud to your actual desktop almost simultaneously. That is not a coincidence. That's a direction the whole industry is headed for. Next up is Z.ai, which is formerly known as Z.ai, which are now publicly traded in Hong Kong. They dropped GLM5 Turbo, and what makes it interesting isn't any single spec, it's the design philosophy. Most AI models are built to be general purpose, and then people try to use them for long multi-step agent workflows. It kinda works, but it's not what they're made for. Z.ai went the other way. GLM5 Turbo was built from scratch with long-chain agents tasked as the primary use case. Multi-step automation, extended tool calls, persistent workflows that don't fall apart halfway through. The numbers? 48 tokens per second, a context window over 200,000 tokens, and up to 131,000 output tokens, and a tool error rate of 0.67. That last one matters a lot for agents. Errors in tools calls compound over long chains. They even built their own benchmark specifically for end-to-end agent evaluation and not just isolated tasks. Pricing an open router is $0.96 per million input tokens. For what it's built to do, that's a good deal. Specialization is a real strategy, and I think more teams should be building this way. Now here's a question. When a developer writes code and says, "This works," how did they actually know? Usually they run tests. They write a bunch of scenarios, check that the outputs look right, and if nothing breaks, then they ship it. That works mostly. But tests only check the cases you thought to test. There's always a gap between it passed all my tests and it actually does what I think it does. Formal verification is the solution to that gap. Instead of running tests, you mathematically prove that the code behaves correctly, the same way you'd prove a geometry theorem. No edge cases slipping through, no surprises in production. You either have a proof or you don't. The problem is that it's been incredibly hard to do. It requires specialized knowledge, a lot of time, and tooling that most developers never touch. Leaningstrol is Mistral's attempt to change that. It's a code agent built specifically for Lean 4, which is one of the main systems used for formal verification. You point it at your code, tell it what the code is supposed to do, and it works to formally prove that it actually does that. It can debug when the proof fails, handle situations when a library update broke something, and translate between different format systems. It's small, with only 6 billion active parameters, but it was trained specifically for this job and not adapted for something general, and on benchmarks that test real proof engineering tasks, it actually beats much larger and much more expensive models. The leading closed-source competitors cost anywhere from $500 to up to $1,600 to run the same benchmark. Leaningstrol costs $36 and scores higher. It's a fully open source under Apache 2.0, so anyone can use it or build on top of it. For most developers, this stuff probably still feels distant, but for anyone writing software where a bug has real consequences such as medical devices, financial systems, aviation, this is the kind of tool that makes previously unrealistic guarantees actually achievable. Finally, quick one to close out. InSpatio published WorldFM, a real-time multi-view spatial AI model that runs entirely on one RTX 4090. That constraint is the whole story. Multi-view spatial models, such as the kind that synthesize multiple camera angles into a coherent 3D scene understanding, normally need serious compute infrastructure. WorldFM does it in real time on consumer hardware. That opens the door for robotics, AR, and spatial computing applications that couldn't afford the compute before. Now, it's still in research stage, but the efficiency improvement is real, and the interactive demos on their project page are worth checking out. Now, here's the thing I keep coming back to after a week like this. Altman said, "Use what we have now to find what comes next, and then you look at everything else. Leaningstrol, WorldFM, GLM5 Turbo, Manus going local. It feels like that's exactly what's happening. Every one of these is someone using the current generation of tools to push a boundary that seemed fixed. I don't know what the architecture after Transformers looks like. Nobody does, at least for now. The Transformer era gave us things nobody predicted. Whatever comes next will probably do the same."